All right, in this lesson, we're going to be talking about more complex graphs of functions. And our main goal is that we're going to be able to describe the domain of a function based on its equation or its function rule, meaning that we should be able to describe the domain without necessarily having to look at the graph. We're also going to be able to describe domain and range of a function from a graph without endpoints, meaning that it's continuing on with some arrows is how we normally see it. So the first semester we deal mostly with linear functions. But in the last lesson where we saw the Thunderball roller coaster graph, we saw that there were curves, so different hills and valleys. So not all functions are lines. And we want to be able to look at those functions and determine the domain without always having to see the graph. So most of the things we're looking at in Algebra 1, unless it's a real life situation that limits us, our domains are typically all real numbers, meaning that x can be anything really that we want it to be. Most of the time, it can be a decimal or a fraction or a negative, unless it's a real life situation. But if we're just given a function, we want to be able to know that the x that we plug in is going to give us a result that makes sense. So there are two exceptions to this general Algebra 1 all real numbers rule. And these are based on rules that you should already know. So the first exception is that we know we're not allowed to have 0 in the denominator of a fraction. So when we have a fraction that has a variable in the denominator, we know that fractions are division. And one of the very first math rules you learned in elementary school, the first time you had actual rules, was that you're not allowed to divide by 0. Can't divide by 0. So that means we're not allowed to have 0 in the denominator of a fraction. So when you have a variable in the denominator, we have to figure out the value that would make that denominator equal 0, and we have to exclude it. So in this case, example 1a, we're asked to find the domain of this function, 1 over x minus 2 squared. So what we have to do is figure out what will make the denominator equal 0. The way that we do that is by actually setting my parenthesis here not equal to 0. So instead of saying x minus 2 equals 0, we say x minus 2 can't equal 0. Because if x minus 2 becomes 0, then I've got 0 squared, which is 0, which means I'm breaking this math rule that you learned way back in elementary. Can't divide by 0. So we are saying x minus 2 can't equal 0. And then we actually solve it just as if it were an equation. So we add 2 to both sides. Those go away. And I have x can't equal 2. And so that's one way that I can actually write my domain. Because saying what x can't be is often equivalent to saying what x can be. So I can say x not equal to 2 for my domain. Now, we said we wanted to be able to determine, in our goals, determine the domain based on an equation, but we did not say we wanted to be able to determine range based on an equation. Range, we really prefer to look at the graph. So this is the graph of this function f of x. So if I want to determine the range, remember that range is the ROI, range output y values, and remember that when we're listing a range, we're looking for a ceiling and a floor. So floor and ceiling. So when I look down, the very lowest value I see is just above 0. I've got little arrows which indicate this is going on. I don't have any end points, so it doesn't look like it's ever touching the 0, but it does look like 0 is kind of a floor value. When I look up for a ceiling, my arrows keep going up, which means that there is none. So if there is no ceiling, that means that it can continue to increase infinitely. So that means it can keep getting bigger and bigger. If we end up in a situation where we either don't have a floor or don't have a ceiling, then that means instead of writing an inequality sandwich, we're just going to write a one-sided inequality. So the lowest value that y can be is 0, not including, but it can be anything bigger because it keeps going up. So because there is no ceiling, that means that my y is greater than 0, because 0 seems to be where my floor is, but again, no equals because it doesn't look like it's touching. And then because there was no ceiling, I don't do a sandwich. I just say, looks like the y's are bigger than 0. And that's the end of it. Now, exception number 2 is for square roots. So by definition, the square root of a number is the value multiplied by itself to give you that number. So hopefully you know that the square root of 16 is 4, because 4 times 4 is what gives you 16. So square root of 4 is 2, because 2 times 2 is 4. So go ahead and write out what the square root of 25 is, meaning what, when you multiply it by itself, gives you 25. Hopefully you said 5 there, because 5 times 5 is 25. So you're thinking easy. What's the problem? Why are square roots this exception? It's because of this. What is the square root of negative 16? In other words, what can you multiply by itself to get negative 16? So you might think 4, but it isn't 4, because 4 times 4 is positive 16. What about negative 4? If this is a negative, wouldn't it make sense that this should also be a negative? But this is a no also, because negative 4 times itself is also a positive 16. And you can't just say, well, I'm going to take negative 4 times positive 4. That's not the definition of a square root. Square root is multiplied by itself, not by something else. So there is no real number that you can multiply by itself to get a negative number. There is actually an answer to this square root of negative 16, but it's something that you'll focus more on in Algebra 2 because it's not a real number answer. So because of that, that means that we are not allowed, just like we're not allowed to have 0 in the denominator of a fraction, we're not allowed to have a negative number under a square root. So here we're looking for the domain of f of x equals the square root of x minus 5. So the part under the radical can't be negative. So just like up here where I said x minus 2 can't equal 0, down here I'm going to say x minus 5 has to be greater than or equal to 0, because that will make sure it's not negative. And then I just solve this for x in order to get my domain. So x greater than or equal to 0 plus 5, which is 5. So x greater than or equal to 5 is my domain. For my range, I like to look at the graph. Now, this is a screenshot taken from Desmos. And Desmos often does not give you the little arrows. So that's one little pet peeve that I have about both graphing calculators and Desmos, is that it doesn't give you this pretty arrow. So I can see, and I'm going to tell you right now that this is a closed circle here on that picture. And what I'm looking at now is to find the range. So again, I'm looking for a floor and I'm looking for a ceiling. So the floor for Y values, again, range Y's, floor, the lowest Y value I see is right here, and that's 0. The ceiling, when I look, okay, the Y's are getting bigger. They're getting bigger very slowly, but this arrow means that it's going to keep going bigger and bigger and bigger. Very slowly, but it is. So there is no, writing the none in the wrong spot there, there is no ceiling this time either, which means if there's no ceiling, that means Y is greater than or equal to, because it's a closed circle, it does touch 0 this time. Y is greater than or equal to 0 would be my range. And notice that if I were just looking at the graph, the domain would work when I'm looking for the walls. Leftmost wall, okay, I hit a wall here where x is 5. When I go for a rightmost wall, there isn't one because it keeps going right. So that means, again, okay, the lowest it can be is 5 and it gets bigger. So it gives us the same idea. All right, now we're going to practice finding the key features of the following functions. So here, when I look at the function rule for A, this is what we call a quadratic equation. It, when you look at it, does not have any of the exceptions, which means that is going to tell us that x can be anything. So that means that x can be all real numbers. So you can either write all real numbers, this is the symbol for that, it's an R with an extra line, or you can use infinity symbols and say x is between negative infinity and infinity, because it can be anything. Range values, I have to look at the graph for range. So first I look for a floor. Looks like I've got arrows going down, so there is no floor. Now I look up for the ceiling, so no floor. Ceiling, oh, I do have one. It stops right here. So the ceiling is 9. So if I have a ceiling and no floor, that means my values all have to be below the ceiling. So Y less than or equal to the ceiling, which was 9. The Y-intercept, so where it crosses the Y-axis, that would be right here. Remember that this should be an ordered pair, so 0, 8 would be my answer there. X-intercepts, where it crosses the X-axis. I have 2 of those, one here, one here. Write them as ordered pairs. So that's -2, 0, and this one is 4, 0. Max, so the max Y value is 9. The minimum, there is none. It keeps going down forever and ever and ever. All right, next one. This is what we call an exponential. Notice that it does not have x in the denominator of a fraction, and it doesn't have an x under a square root. So that means that my domain, again, is going to be negative infinity to infinity. This is just our way of saying that x can be anything. All right, now when I look at my range, I can see here that my floor looks like it's going to 0, but it doesn't have an exact point on 0. It has an arrow. So that means that it doesn't actually touch 0, but that is my floor. So from 0, and then when I look for a ceiling, there isn't one. It's going up forever and ever. So Y is greater than 0. All right. I want you now to go ahead and do the y-intercept. So look at this graph, touch where it crosses the y-axis, and write it as an ordered pair. All right, hopefully you said 0, 1, because that's the point, the ordered pair right here, and that is my y-intercept. For x-intercepts, because this never actually gets down to touch the axis, that means that there isn't one. Same idea with max and min. I don't get a minimum or maximum value because I've got arrows. This arrow, the y values are getting closer and closer and closer to 0, but there is no minimum. And up here, the values just keep getting bigger. There is no maximum. All right, last one. This is a linear function, y equals 2x minus 1. Again, the two exceptions I look for are, is there a variable in the denominator, which there is not? Is there a variable under a square root? There is not. So that means that negative infinity to infinity, that all real numbers, is my domain. For my range, I've got an arrow going down, so no floor. I've also got an arrow going up, so no ceiling. If I have neither a floor nor a ceiling, that means that my range is also negative infinity to infinity, meaning that y can be anything. Y is all real numbers. All right, now when I look at my y-intercept, where it touches the y-axis, looks like about right there. So I would call that point 0, negative 1. The x-intercept looks like it's halfway to 1. So I would say 1/2, 0. Maximum, well, it keeps going on forever and ever, so no max. Same thing with min. On and on and on, and never ever ending. So you can see when you've got arrows going both directions, up and down, what that does to our max and min. Here, I only had arrows in one direction, and so I had a max, but no min. All right, so hopefully you understand the two exceptions and you've gotten some more practice with those key features.